My name is Olivia, and my project was on the dynamic photoluminescence response of dipole modulated rare earth doped core shell nanoparticles and and how they react to local changes in solution pH. Quantifying luminescence of nanoparticles in biological applications. So the focus of my project was on how these nanoparticles would react to different environments, which can include changes in pH. And so there are different methods to rare earth fluorescence, such as up conversion and down conversion. And for this project, down conversion it was used where you are shining a high energy light to a crystal and you get a low energy light in return. And this is important because in potential biological or environmental applications, the environment such as the pH can be different from neutral pH. So it's important to see how these nanoparticles react to the different pHs. So this is a slide about previous work in this topic. And using this as a reference, after synthesis, the PL properties were scanned to see whether the excitation spectra looked similar. So after synthesizing the nanoparticles, the photoluminescent properties were scanned. And so the profile of the excitation scan for the nanoparticles are somewhat similar to previous studies. However, it's a little bit different because in this project, after synthesizing, the PL properties were scanned in powder form, while in previous studies, it was done in solution. And the reason why I'm comparing the as synthesized particles and annealed ones is because annealing can remove the impurities from the crystal structure. So it can improve the photoluminescent properties, as you can see on the emission scans. And completing these scans are important because they can be used as a reference in future studies or different pH studies later in this project. So generating a pH titration curve. The reason why we're looking at pH is because it can affect the dipole moment of the nanoparticles, or it can somehow affect the ligands by detaching them from the surface of the nanoparticle. So the first thing in the pH studies that I did was creating this titration curve. In comparison with household items such as vinegar, which is a weak acid, and baking soda, which is a weak base, in this study, sodium hydroxide, a strong base, and hydrochloric acid, a strong acid, were used to generate the titration curve. The reason why the curve looks like this is because once the curve is nearing the pH of 7, which is the point of neutralization, even the smallest bit of base can create the jump from the neutral pH to the more acidic ones. And demonstrating this curve is important because it contributes to an understanding of how these bases and acids can work together. So the effects of pH on photoluminescent properties of samples. After synthesis, the surface of the nanoparticles were functionalized with aminobenzoic acid and nitrobenzoic acid. Functionalization is important because it can change the properties of the crystals. So you can change it however you want according to what situation you are applying them to. So seeing how these ligands react to the different pHs can be important. The general trend that was shown in the results show that at a higher, more basic pH, the intensity of the excitation spectra increases, and at a lower, more acidic pH, the intensity is quenched and the peaks are less pronounced. Comparison study between samples at a given pH. So on this slide, the plots show the different types of samples at specific pH points. And the reason why 4, 7, and 10 were chosen is because 4 was the acidic extreme of the pH range that I tested, and 10 is the basic extreme, while 7 is the neutral point. And as you can see, when comparing the functionalized particles to the non-functionalized ones, the functionalized aminobenzoic acid and nitrobenzoic acid nanoparticles have a shift to the right, which is called a redshift. And so in conclusion, these nanoparticles were synthesized and then functionalized with aminobenzoic acid and nitrobenzoic acid. And in order to see how these nanoparticles would react in different environmental situations, the effect of solution pH was observed. The trend shows that at a more basic pH, the intensity of the excitation spectra increases, and at a more acidic pH, the intensity of the excitation spectra is decreased. And detecting these changes may be important in biological applications, such as sensing for biomarkers in tumor environments and toxins from algal blooms. Some future directions include repeating this pH study portion of the project to see whether the general trend is still shown. And because we don't really know why this is happening, looking into existing literature can be helpful to see why it's happening and possibly replicating that work to see whether it's still shown. Temperature studies are also a possible future directions, and expanding the project to a core shell nanoparticle or sensing experiments with biotin and avidin. That's all.
All right, thank you, Olivia. Dr. Constant?
Thank you. That was good. The profiles, while they changed with the spectra, while they change with pH, they remain very similar, right?
Yes.
So you can pick them out. You can still pick them out. What happens when you actually make this measurement? Does it get, is there noise in the signal?
So, could you repeat that?
Okay, you have a nice clean experiment here where you're testing the different pHs and you're getting a spectra. Would it be different in practice?
So I think it depends on which, so completing the excitation scan, you need to choose an emission wavelength to scan it from. So depending on that, that may change a little bit. And also these graphs were normalized. So right after just scanning them, it could be a little bit more noisy, or the profiles could look a little bit different.
Oh, and I also see that the scale is different in that pH 10 plot by a factor of 10. Okay, that helps. That really brings it out now. I can see that. Okay, I got it now, because they look very similar until I saw that scale change. I'm glad we went back to this slide. Thank you.
Okay, thank you.
Thank you, Dr. Constant. Dr. Lima?
Hey, Olivia, that was a nice presentation with a lot of information, and the last slide about future directions was also really good. So the question I have is about future directions, and you mentioned that you would like to extend your study by maybe going more acidic and more basic, so getting out your pH beyond, below or and above 10, essentially. What do you think your trend will do based on your experiments between pH 4 and 10, and why do you think that trend would or would not continue?
I think the general trend may continue, but it may be slightly different at more extremely acidic or more basic pHs. In one paper that I looked through a little bit, it said it may be due to energy transfer, but other than that, I couldn't really find reasons on why. So looking into that would be helpful and interesting.
Okay, thank you.
Thank you.
All right, Boz, we have time for one quick question from you.
All right. I was going to ask this question a different way, but I'm going to go ahead and, yeah. Explain to me exactly what you did and why you did it in terms that a 10-year-old could understand.
So I made these particles which have a structure where there's an inside called the core and an outside called the shell. And then on the shell of some of the nanoparticles, we added these other organic molecules that are called aminobenzoic and nitrobenzoic acid. And those are called the ligands of the functionalized surface. And then using different pHs, such as in household items, vinegar, which is known to be acidic, and baking soda, which is known to be basic. We use those, but we use acids and bases like those on a higher, more extreme scale. And then we saw how it affected how the core shell nanoparticles performed.
I know that was a tough question to answer on your feet there, or on the spot there, I should say. But thank you.
All right.
Thank you.
Thank you, Olivia. You can go ahead and stop sharing. Our final.
Olivia, I have one quick question. Your sources, your literature, did I miss something?
So the main source I used was on this slide down here. Yeah, that was basically the one that I looked at.
Okay, that's what I was looking for. I missed it. Thank you.
Okay, thank you.